Hi everyone, thank you for joining. I wanted to start by thanking the organizers of this event for all of their work and for giving me an opportunity to speak to you. I unfortunately can't join live at the scheduled time since I'm in the States, but I am more than happy to follow up with you offline with any questions you may have. I'll be sure to share my contact information at the end. So today I'm going to be talking about applied natural language processing. How do you use AI in real user-facing production applications? This is meant to be an introductory talk which gives an overview of applied NLP, but I will also give a tutorial on using these concepts to build a chatbot as an example use case. I'll start by briefly introducing myself. I got both my undergraduate and master's degrees from Stanford, focusing on AI and NLP. While I was there, I got an understanding of the academic perspective of solving challenging NLP problems with state-of-the-art models. Then, about 4 years ago, I joined a startup called MindMeld, where we built conversational interfaces, voice assistants, and chatbots for various enterprise customers, including companies like Starbucks, Uniqlo, McDonald's, and others. About 3 years ago, we were acquired by Cisco and have continued to work on NLP problems for various production applications. For example, we have a voice assistant for meeting rooms and have worked on other use cases like customer support, document search, meeting highlight extraction, and more. We also open sourced MindMeld, which is our NLP platform for building conversational interfaces. So during my time at MindMeld and Cisco, I've learned quite a bit about applied NLP and deploying production-ready models. Today, I'm going to start by talking about the motivation. How is applied NLP different from theoretical NLP, and why should you pay attention to those differences? I'll introduce some core concepts of NLP that are broadly applicable to a variety of use cases. And then I'll go through some best practices for collecting data to build your own application and talk about some popular toolkits and frameworks you can use. I'll then walk through an example use case of a conversational assistant that uses these concepts with the MindMeld platform. And finally, we'll discuss how to improve your deployed systems and models over time in a secure way. So starting with the motivation. As I mentioned, there are different challenges between academic or theoretical NLP and practical or applied NLP. And while there are quite a few online resources on the academic side, things like state-of-the-art research from recently published papers, lessons on AI and NLP theory and fundamentals, blog posts on how to download and try out the latest models, while there's a lot of information there, there isn't as much information on how to use all of this in practice in a real-world, customer-facing application. So that's what I'm hoping to share with you today. I'll start by outlining some of the key differences between academia and industry, the first of which is data. Production applications may have very limited data compared to standard research data sets. For example, Squad, a popular QA data set, has over 100,000 questions, but you may only have a couple hundred question-answer pairs to set up your system. Your data may also be noisier or have different characteristics than standard data sets. For example, it could contain a lot of domain-specific terms like product names. And because of this, out-of-the-box models may not work well. The second is the need for reliability and interpretability. There has been a trend towards deep learning models which perform really well on large amounts of data, but they may pick up trends in your data that you don't want them to, because real-world data naturally has bias. For example, a lot of companies have shown up in the news for accidentally building sexist or racially biased models. When your model is learning on its own from data trends and you're not explicitly specifying features, it can be harder to unlearn those biases and fix the models quickly. So you often want models that are more consistent, more engineered, and more interpretable. Next, academic papers tend to focus on a single component of a larger problem. And while these components may work well individually, they often break down as part of a larger pipeline due to a sort of compounding error effect. For example, if your speech recognition is off and it recognizes the query call Nagasundar, which is a person name, as the text call not a sender, then it makes it really hard for the NLP to understand what the user is asking and then complete the task. Also, in academia, accuracy tends to be the gold metric that you're constantly trying to improve. But in practice, you care about usability and scalability. Device constraints play a role, inference time plays a role, and a lot of times these factors, which contribute to how usable your application is, are more important than minor accuracy improvements. So the way that you tune your models is different. And finally, you care about security. AI is a data-driven field. The more data you have, the better your models will be. But you have to be careful about keeping this data secure and not violating customers' trust. This has also shown up in the news with data breaches and a sentiment of users feeling like companies are spying on them or listening to them all of the time. So now that you know about the differences between AI theory and practice, I'll give you some tools to help solve these problems in practice, starting with an overview of core natural language processing concepts for those less familiar with the space. So at a high level, classic machine learning models tend to rely on feature engineering. Developers use their domain knowledge to come up with meaningful features to extract from their data. And this lends itself to more interpretable models because you know what features your model is learning from. One of the great things about deep learning approaches is that you don't need to do as much of this feature engineering. Once you vectorize your data, the model learns what is important from the data on its own. But this requires more data, and the larger or more complex your problem definition is, the more data it requires. It's also harder to pick and choose what trends from the data your model picks up on, especially if you treat it as an end-to-end system. And it generally requires more compute power if you are training a model from scratch. Deep learning is useful and powerful, but it can get you into trouble if you treat your production models as black box end-to-end systems. So the solution to many of the problems that I outlined, problems like having less available data, wanting more interpretable models that are easy to debug and update, and possibly needing to train or run a model with limited compute power, the solution to those problems is to have more defined models. Instead of a black box end-to-end system, break down the problem into subproblems. To be clear, I'm not saying you shouldn't use deep learning. Like I mentioned, it's very useful and powerful. But instead of using a single end-to-end black box system, break down more complex problems into a series of models that you can evaluate well. A pipeline of simpler models can work well reliably, even having being trained on smaller data set sizes. And then over time, as you collect more and more data, you can start using more complex models for each of these subcomponents. So with that in mind, I think most practical applications of NLP can be modeled as 4 general categories, and more complex NLP problems can be handled with a pipeline of these models. So I'm going to walk you through each of these types of models now. The first of which is text classification. For all NLP problems, the input is a piece of text. And with text classification, you take that query or piece of text and output a label. One example application of this type is domain classification, or recognizing the general field or category that a query belongs to. For example, if your predefined domains are weather, news, sports, smart home, etc., and you want to classify the query, what is the weather in San Francisco this weekend? The model can predict the label weather. Another example is sentiment analysis. In this case, given a piece of text, you want to output the labels of positive, negative, or neutral. For example, a query like fantastic movie, was laughing the whole time, which is, in this case, a movie review, that should be classified as positive sentiment. Highlight extraction or meeting summarization or topic summarization can also be modeled as a text classification problem. For every sentence in an article or a meeting transcript, you can output a binary label of whether that was a highlight or not. Some models that you can use for text classification are logistic regression, SVM, random forest, decision trees, or deeper neural networks, of which there are many network architectures available. For features, you can use n-grams, which are sequences of n words or tokens in the order that they appear. Bag of words, which is a count of all of the words in your text without paying attention to the order. Word shape are orthographic features that take into account if there are capitalizations, punctuations, numerics, etc. The length of your text itself can be a feature. Gazetteers are indices or dictionaries which contain domain-specific vocabulary and the frequency at which they occur. So a gazetteer match feature is whether or not your text appears in your gazetteer and what that frequency is, which can be really useful feature. And for neural network models, your input can be a character, word, or a sentence level embedding, which is a vector representation of those terms. And while it's good to be aware of these models and features, there are many libraries, toolkits, and frameworks out there that implement these models and feature extractors for you. So you very rarely have to implement these yourself. Most of the work you'll do for AI in practice will be framing the problem and collecting the data. And the model itself will often be a one-line call to a library. So I wouldn't get too caught up in the details of these, especially if you're just getting started. The next type or category of models is sequence labeling. Again, your input is a piece of text, but now you output a label for every word or token in that text. Some applications of this are entity recognition and part-of-speech tagging. Entity recognition, for example, is the problem of extracting keywords or phrases from the text. In this example, we would like to recognize the entities of movie title, release date, cast, director, etc. So given an input, what are some Tom Hanks movies released in 2015? Your sequence labeling model would label each of these tokens as being one of these entities or other. Then this is able to give us the final output of extracting Tom Hanks as a cast member and 2015 as a release date. For reference, some sequence labeling models you can use are MEM, Maximum Entropy Markov Model, CRF, or Conditional Random Field, LSTM, BiLSTM, or various other recurrent neural networks. Some of the features you can use are essentially the same as the features that I described for the text classification problem. Next are sequence-to-sequence models. For these, you can take text as input and you output a sequence of tokens of arbitrary length. Some applications for this are machine translation and natural language generation. Machine translation requires a lot of data to get right, so you're generally better off using a pre-trained model or one available through an API. Natural language generation generally doesn't work well enough to be used in production, So people usually use more rule-based templated responses instead. So I won't go into too much of the detail on the models here. The last category is information retrieval. This isn't a trained model per se, but it's one of the backbones of applied NLP. Information retrieval is the problem of retrieving a document from an index or database based on a search term. Some applications of this are question answering, document search, and entity resolution. As an example, say someone wants to know which artist played the song Bohemian Rhapsody, and you have an index which contains songs and artist names. You can search that index with the song title Bohemian Rhapsody to get the document which has the artist field populated as Queen. Now this is more complicated than a simple database lookup because it takes into account fuzzy matching. You can use, for example, matching on normalized text with special characters removed. You can also use n-gram features for phrase matching or partial phrase matching. Character n-grams are useful for partial word matching and for things like misspellings and typos. You can also use deep embeddings, semantic embeddings, which are useful for matching in the semantic space. So matching two phrases which mean the same thing but textually look very different. For example, say you were searching for spaghetti marinara with the search term pasta with tomato sauce. And you can also do matching in the phonetic space using phonemes. And this is useful if you have speech recognition mistranscriptions to still be able to recover the correct documents or fields. So in summary, the 4 categories we talked about are text classification, which outputs a single label for a piece of text, sequence labeling, which outputs a label for each word or token in the text, sequence-to-sequence models, which have inputs and outputs of arbitrary lengths, and information retrieval, which is essentially full text search. There are some areas that I didn't cover. I didn't touch on unsupervised models at all, but in my experience, the majority of practical NLP applications can be modeled as one of these 4 categories, and for more complex problems, a combination of them. So that was a quick overview of fundamental NLP concepts that you can use to model your problem. Once you've decided what problem you want to solve and how to model it, the next step is to collect data. When collecting data for NLP, you want to collect the text itself and labels for that text so that you can train your models. But before you jump into collecting data, it's always a good idea to first check if there are any pre-trained models that you can use out of the box. Hugging Face is a popular platform that has implementations of many state-of-the-art models. Core NLP, Spacey, and NLTK are platforms that have implementations of many NLP basics and fundamentals, such as named entity recognition, part-of-speech tagging, etc. And you can always do a simple Google search to look for additional models as well. Even if these pre-trained models don't perfectly fit your use case, they can still be useful for fine-tuning or as features to your models. Now, if you are training a model, first check to see if there are any existing data sets available. There are a lot of open source data sets from academia that you could use at least as a starting point. You may also have data within your organization that you may want to use, or you may be able to scrape data from a website or another publicly available source. So try to see if you have data available, but if not, don't hesitate to generate a new data set from scratch. If you are generating a data set, one thing that might be useful is to take advantage of crowdsourcing tools. For example, Amazon Mechanical Turk, Crowdflower, Upwork, etc. If you are collecting data via one of these tools, it's important to describe your task well. If you are too specific with your description, you will get lots of very similar looking data. And if you're too general, a lot of the data you get may be irrelevant or not useful. And in order to get at that right sweet spot, it's helpful to iterate. Work in small batches to collect your data, see how the results look, and update your task description accordingly. Some of these data collection platforms help match you with workers who are trained in your specific use case. And this is really useful if you want clean, consistent data. For cases where you want more variation or generally want to see how the public responds to certain prompts, it may be better to go with tools like Mechanical Turk that anyone can contribute to. You can also do things like target specific geographic areas when creating the data collection tasks, so that you can get a variation in slang and regional language that people might use. It's also important to implement validation or sanity checks. Sometimes people, especially on these more open platforms, will try to complete a task as quickly as possible. So they'll just do things like keyboards matching or enter all single characters like all A's, or just leave some data fields blank. So you can target workers with better ratings to try to mitigate this problem, but even then it's important to implement some validation checks. For example, you can make sure that the length of the text is similar to the length that you are expecting. Make sure that it's not just white spaces, and make sure that, for example, if you're collecting English language queries, make sure that at least some of those words appear in an English language dictionary, and things like that. In addition to the text itself, remember that we want to collect labels for our models. It's incredibly important that these labels are clean, because without clean labels, our model can't learn. If you use crowdsourcing tools or data teams for this, you should give contributors some training and evaluation before they start labeling. And this can be as simple as a few example queries and a few queries that are used as a test to make sure that the labelers understand the task. You can also have multiple people label the same queries and only accept labels with a certain level of agreement. And once you have an initial model, you can help speed up labeling time by using the model predictions to bootstrap your labels. Then instead of a label generation task, it becomes more of a verification task, which is generally faster and easier to do. And finally, if you don't have any other resources, you can create and label your data yourself or with an in-house data team. And this can be a great way in general to bootstrap an initial model. It also gets you thinking more closely about the data you are trying to collect, and then over time, you can add more and more data to this data set based off of things like log data from user interactions. So now you've framed your problem and collected your data. The next step is to train your models. I'm going to give you an introduction to some popular toolkits and frameworks that you can use to do that. So to train a model, scikit-learn or sklearn is a popular toolkit for classic models that we talked about, like logistic regression, support vector machines, random forests, etc. For neural networks, you can use tools like PyTorch and TensorFlow. More specific to NLP, we mentioned these toolkits before in the context of pre-trained models, but they are also very useful as feature extractors. So you can use these toolkits to generate features from your text, like n-grams and bag of words, and then feed these feature vectors into scikit-learn to train your model. For more complex problems that involve multiple NLP components, namely conversational interfaces, there are a variety of platforms available that you can use. These platforms have a lot of preset defaults or feature extractors and models and have the whole pipeline set up. So you can, so all you have to do is provide your data and implement any custom logic. Even if you're not building a full conversational interface, these platforms can be really useful for their subcomponents as well, like just for question answering or unstructured search or for entity extraction. And finally, there are tools on the infrastructure side that can be particularly useful for AI. Elastic including Elasticsearch, is useful because not only is it a database, but it is also a full-text search engine with a lot of information retrieval capabilities built in. AWS, Google Compute Engine, and other similar platforms are great for cloud compute, where you can train your heavier models efficiently. Kubernetes is a platform for easy development and scaling of your systems. And DVC is a tool for data versioning so that if you have multiple people training models, they can be synchronized on the data they are using and version that data as it changes. So in the time frame for this talk, I unfortunately can't give a hands-on tutorial for all of these different tools and frameworks, but all of them have lots of documentation and tutorials available online. And hopefully having the background context from this talk, that will help you decide what tools to look into for the problems that you are trying to solve. But to make all of this more concrete, I'm also going to walk through an example application which uses the concepts we've discussed so far and provide the coding tutorial for you to try it out yourself. More specifically, I'll be giving you an example of building a food ordering conversational interface with the MindMeld platform. So this is a complex problem, so it involves a pipeline of multiple models shown here. And this sequence of components is not unique to the MindMeld platform. All major players in the space use a similar pipeline, so it's really become an industry standard. To follow along with the coding examples, I've created a Google Colab notebook. Hopefully you have the link for that. I've also written it here. You can go to bit.ly/mindmeld-tutorial. Make sure that you go to File and save a copy in Drive in order to get your own copy of this notebook. And then you can run this yourself on your copy as well. So the first step is to install the MindMeld platform, and we'll go ahead and kick this off since it takes a couple minutes to install. And then once that install, you can also install Elasticsearch. Note that the syntax for installation here is specific to getting this working with Google Colab. If you want to have the syntax to natively install this on your own machine, you can look at the instructions in the documentation here. And it'll take just a minute for the Elasticsearch server to be set up. And once that is set up, then this command should return true. So we'll just give that a minute, and now it is returned true, so the server is set up. We also need to run the numerical parser. This sets up another server which takes care of the resolution of numerical entities like times and dates and quantities. And then The last step to get this set up is to download our example application. And in this case, we are going to work through a food ordering application. The example applications in the MindMeld platform are called blueprints. So you would run the command line command MindMeld blueprint food_ordering, and that downloads and sets up this application. So we will go ahead and run that now, and it'll take just a minute to download and run. Great, so now that has created that application, and you can see that the food ordering folder was created, and it contains all of these files, which include your config.py, domains, entities, etc. And we'll start by just building the application by running this command python-m food_ordering build. And what this will do is it will load in all of the training data in this example application and train all of the models with the preset defaults that are provided. So this will allow us to be able to just load and run the application, but I will also walk through each of the components and what you would need to do to build this from scratch. So this will take a few minutes to run. While it is running, I'll go ahead and go back to the slides and start describing our first component, which is the domain classifier. This is a text classification problem like we talked about. Given an input query like, what is the weather in San Francisco this weekend? This can classify it as a domain or a broad area of general knowledge. Next, we have an intent classifier, which further specifies this query based on the action that the user is trying to take or the task that they're trying to complete. For example, in the query, I'd like spicy pad thai and spring rolls, please. We know the domain is food, but the intent classifier can further specify this as a build order intent. The third model is a entity recognizer, which is a sequence labeling model. So in this example query, which we talked about before, what are some Tom Hanks movies released in 2015? You want to extract Tom Hanks as a cast member and 2015 as a release date. Role classifiers are another text classification problem, which are useful for further specifying entities when needed. For example, in the query, schedule a meeting with my manager from 11 a.m. to noon. Both 11 a.m. and noon are time entities, but they can be further classified as start time and end time. Next, we have the entity resolver. This is an information retrieval problem, and it resolves the text from the extracted entity into a canonical form by searching against the dictionary database or index of canonical entities. For example, in the query, I'd like spicy pad thai and spring rolls, please, we find that the closest match for spicy pad thai is pad thai extra spicy with this canonical ID value. And similarly for spring rolls, we find fresh spring rolls in the database with this ID value. And this is really useful to have the canonical forms because they can then be used to make an API call or to make some follow-up requests. And finally, we have the language parser. This model will group together entities which are related to each other. For example, in the query, I want a pepperoni pizza with extra cheese and 2 Diet Cokes from Domino's. Extra cheese is modifying pepperoni pizza, 2 is a quantity for Diet Coke, and Domino's is just in its own entity group. And this model is a weighted rule-based model. So let's look into the code and how this can be used. Okay, so it looks like our model has completed building. So we can go ahead and run this command to load in the trained models. And this NLP object contains kind of all of the components that we just went over. of our natural language processor. So when we run nlp.process, this will give us the output of those models. And this is the example query, I want some pad thai. So here it is classified as the ordering domain, the build order intent, and then we see that we've extracted the entity of pad thai, which is a dish, and we've resolved that to a list of possible values, the top being this specific pad thai with this ID number. So the process function kind of takes care of everything for us, but if we would like to go in and experiment with these various models, we can also do that. So we can get the domain classifier from this NLP object, and you can see here that for this example application, we only have a single domain. For the intent classifier, we do have a set of multiple intents, and we can get that intent classifier object as well. So in order to ingest the training data, because it's a little bit hard to view files in this Google Colab notebook, I also just opened up this same food ordering application in Sublime Text locally. You can see how we input data into an application if you're building it from scratch. And the way that you do that in this platform is you have a folder of domains and intents, and you use that folder hierarchy structure to label the domains and intents. So to be consistent with what we were looking at in the notebook, you can see here that we have a single domain of ordering, and within that you have all of these intents of build order, help, place order, etc. Within each of these intent folders, you have a train file and a test file. And these contain, the natural language queries that are used to train the domain and intent classifier models. So here, all of these queries, great seeing you, hello, what's up, greetings, how's it going? These are all for the greet intent. And just by existing at this place in the folder hierarchy, these are labeled as the greet intent and the ordering domain. You can also label entities by using this text markup format. So if you have these braces, this means that normal cheese pizza is labeled as a dish entity, extra cheese is labeled as an option entity, extra sauce is also an option. If you have a further specified role for that entity, you can label that with a second pipe. So in this case, make that one plate of vegetables and so on. Here, one is a number entity, and it's further specified as a number of orders role. And that's to differentiate between orders versus quantity. So differentiating between a 12-ounce drink versus 12 drinks. So once all of your data is labeled and placed here, you can start experimenting and evaluating with these models. The way you do evaluation is simply running this .evaluate command on the classifier that you would like to inspect. So in this case, let's run it on the intent classifier for the ordering domain. And here we see that it gets a score of 95.27% on the test data. We can also further print out additional statistics, which will give us metrics like F1 scores, class-based statistics, and a confusion matrix. Now, let's say we want to further experiment with this model. We can see what the current model is by looking at the config. Here we see that it is using features like bag of words, edge engrams, gazetteer matches, and it's using the text classifier model type of a logistic regression. And it is doing cross-validation parameter selection. So now say we want to update some components of that. Let's say we want to update the features. Let's again see what the current features are, and maybe we want to add some features. So here I want to enable stemming, and if stemming is enabled, maybe edge engrams are less useful, so I'll delete that. And let's say I also want to know the word shape and use that as a feature. So I can go ahead and add that line here. And the specifics for what features you can add are all available simply on the documentation. Let's go ahead and fit that model, and to fit it with the new features, we just pass in that dictionary to the features parameter. And then that will take a few minutes to fit because it is running cross-validation. So that will take a couple minutes to run. In the meantime, I can go ahead and talk a little bit more about some of the data you need for the remaining two models. So we talked here about how you label your data for the domain, intent, entity, and role classifiers. Now for the entity resolver, which is an information retrieval model, you have this entity folder. And within that, for each of your entity types, you can include a mapping.json file. And this is represents a database which has all of the canonical values for your entities. So, for example, for your dish entities, these are all of the canonical values of the dishes that exist in this application. It has their ID numbers, their canonical names, and then a whitelist or a synonym list, which includes other ways of saying that canonical name. In addition, you can include these gazetteer files, which are just a dump of general kind of dish vocabulary. And these gazetteers can be used as a feature for training your classification models as well. And then the final component in the natural language processor is the language parser. And for that, we don't have any training data per se. Instead, we can specify certain rules or heuristics that we observe and how we want to group entities. So this is an example of what that parser config would look like. Here you would specify dish. For the dish entities, options are usually grouped with dish names, and the linking word between options and dish names is often with. So you might often say like, pizza with pepperoni or pad thai with tofu. So you can specify kind of rules and heuristics like that, and then based off of that and the additional default rules that exist in the platform and observations on the data, you can get a pretty accurate parser. So those are all of the NLP models. It looks like this is done running. So now again, we'll continue with how we evaluate the intent classifier model. And so now with these additional features, we have slightly improved our model accuracy. And we can again print out all of those evaluation metrics and statistics in order to make any additional changes that we would like to try out with our features or model types. So yeah, that's an overview of how you can experiment with these models, and the syntax for experimenting with all of these models, the domain, intent, entity, role, all of the classification models, whether that's sequence labeling or text classification, they all have the same syntax. So you can load in the model you would like to inspect. You can always look at the dictionary of the configuration, and then you can run evaluation and print the statistics and experiment with them the same way we just did with the intent classifier model. Now for the entity resolver, that is a information retrieval model, so there are no test data statistics to generate, but you can try out the entity resolver and see how it works as an independent component by running, loading in that resolver and then running this predict on some search term or piece of text. And here with gluten-free pepperoni pizza, we can see that the top returned dish is a pepperoni pizza, gluten-free. And yeah, so these are ways that you can go in and inspect each of these models, but overall, NLP process will run this whole sequence of models for you, and you can see the output of all of those models. And in this case, so we see that this is an ordering domain for I would like a wrap and 2 chicken kebabs. And you can also see for the entities that the number of orders is grouped together with the number, like the 2 entity is grouped together with this chicken kebab entity, as we expect. Okay, so those are all of the components that are used to extract information from the user query. Now, the remaining components, the question answer, which leverages the knowledge base, and the dialogue manager, are about answering the user's question and responding back to the user in natural language. So the question answer component is, again, an information retrieval model. In this example query, the user has not yet specified which restaurant they would like to order from. So the question answer can be used to search against the knowledge base and find restaurants at which these dishes are available. And in this case, that returned 2 possible options, Siem Royale and House of Thai, with their ID values. Then the dialogue manager is used to construct a response in natural language that can be returned to the user. And like I said before, this natural language generation is not very reliable in production, so we generally use rule-based templates. So this example would have a template of, great, I found blank restaurants that match your request. Would you like to order from blank? And then that value of 2 and the names of the restaurants would be included in the response that's returned to the user. And finally, we have an application manager, and this is just an infrastructure component which receives the client request from a supported endpoint. It processes the request by passing it through all of the MindMeld components, and it returns that final response back to the endpoint once the processing is complete. Cool. So if you would like to see how the question answer works, we have an example here, and this is looking at our index or our knowledge base for restaurants. So this is the format of the restaurant object. It contains categories, the ID, the cuisine type, some metadata on the menu, the name of the restaurant, and reviews, and so on. Now, if we would like to search an index, in this case, let's search the menu items with a search term, in this case, cheese pizza, then we can see what the most relevant response is. And here we do see that the top response is a cheese pizza dish. We can also search an index and filter it by some constraints. For example, if the user had said, I would like to order cheese pizza from this restaurant, and that restaurant name was resolved to some ID value by the entity resolver, we can then filter based off of that value. And in this case, we find a cheese pizza dish at the provided restaurant. We can also use the question and answer to sort results based off of some user-defined preferences. Let's say they said they want a cheaper priced option. We can sort by price, and then we see here we again get something that matches cheese pizza, margherita pizza, and this has a cheaper price of $10 versus $22 or $13 that we were seeing before. For using the question answer and the dialog manager, that logic goes or is imported into this init.py file. So that's what that looks like. Let's look at it in Sublime so it's a little easier to read. You can create these app handlers which can execute a chunk of logic based off of the classified values of the NLP models that we talked about. So in this case, we're saying if our natural language processor classifies a query as the greet intent, we want to execute this chunk of logic. And what happens here is that we create a prefix of hello or hello comma name if the name has previously been specified by the user and is stored in that context. Then we get some suggestions of restaurants by using the question answer to get from the restaurant knowledge base, and we store a list of their names. And then we respond with this templated response. So we say hello, which was our prefix. Some nearby popular restaurants you can order delivery from are, and then input the 3 suggestions that we just got from the knowledge base. And so that is how you implement, the question answer and the dialog manager logic in order to make this a usable application. So now let's try out the full application running end to end. So this is loading in all of the trained models, and now I can say, hi there. It gives me some popular restaurants. I can say I want pizza, and let's say order from Fire Trail Pizza, and it has their one order of margherita pizza for $10. I can say I also want a pepperoni pizza. So now it has one margherita pizza, one pepperoni. Would you like to place the order? And I can say yes. And it says, great, your order will be delivered in 30 to 45 minutes. So you can play around with this application. Note that this is an example application meant to be a starting point. It's not fully production ready, but it's a great way for you to get started building your own application. So that was a lot of information, but I hope it was a useful example of how you can use these concepts in a real application. You now have an intro to the resources you need to train and deploy a model, and we walked through this example, but the key to intelligent ML systems is to improve them over time. A lot of the leaders in the AI space have become leaders by continually improving their models from user data. But as an organization, it is essential to do this in a secure way. The most important thing to start with is communication. You should clearly communicate to users if their data will be stored, for how long, who can access it, and what it will be used for. Even if you are abiding by these data policies, if users are unaware of these agreements, it may come across as spying. And this communication can be done in a variety of ways. You can do it during onboarding when people first start using your application. You can also publish white papers on generally your data policies. And you can include in the FAQ sections of your websites what these policies are and advertise them anywhere else that is appropriate. But how do you come up with these data policies? The first thing that you should think about is what data needs to be stored, and specifically, what do you need to improve your systems? Can you store certain extracted metadata or trends, or do you need to store all of the raw data itself? And you want to only store what is essential, and you want to remove any sensitive or personally identifiable information. The next thing to think about is how long will this data be stored? Can you get what you need from it in a shorter amount of time and then discard any extraneous data? Or do you need to keep storing that data until the point of time that the user requests it to be deleted? Also, who will be able to access the data? People will be more comfortable if their data is never read or looked at by humans. People aren't kind of reading their conversations or their requests. But if that isn't possible, if you can limit the team, the number of people that can access the data, that will also make it more secure. So if there's only a very small team of highly trained individuals who can access this data, then that will make it more secure. And finally, think about what will this data be used for. If it provides value to the end user, they are much more likely to be comfortable with you using their data. So whenever possible, if you can provide some useful reports or analytics on the application to the user, that's always a good idea. And if you can show measurable improvements in your models over time, that will also make a case for being able to store this data. So once you've defined your data policy, you need to build a secure data pipeline which can enforce this policy. In order to do that, you want to do things like keep track of information like what user this piece of data came from so that you can delete that data if they ask for it to be removed. You also want to be able to enforce permission, so only authorized individuals should be able to access the data stores. You can also build models to remove sensitive information. For example, if you don't need to store person names and those exist in your data, you can use an entity recognition model to recognize those person names and replace them with a generic token. So this is an example pipeline. Your user queries are passed to the model and the response is returned back to the user. And you likely want to store both the user query and the model output. And that can initially be temporarily stored in a secure cache until you can process those logs. That processing may involve removing any sensitive information or removing any data that you don't need to store long term. And then these process logs can be stored in a more permanent data store, which only certain users have access to. You can also have a tiered approach. So if you have some extracted trends and analytics that are less sensitive, this could be stored in another data store, which can be accessed by additional users. So we've talked about how to collect user data. Now let's talk about how to use that data to improve your model. One efficient way to do that is with active learning. In production, raw data is cheap, but labels for that data are still expensive. Active learning is the process of selecting the best queries to label first in order to improve your models most quickly. And that selection strategy is largely based off of selecting queries that your model is currently most uncertain about. Those are queries that are kind of at the labeled boundaries, and by adding them to your model will improve faster. So you can see in this example graph that in both cases, in both of these lines, we are adding queries at the same rate, and they are both improving. But by adding them by randomly selecting them from the logs, it improves less quickly than if we select them using an active learning selection approach. In order to do active learning on a regular basis, you can build out a semi-automated pipeline. So once logs make it to that more persistent data store, you can select queries using your active learning technique. You can then bootstrap these queries based off of your current models to get some labels. And once those labels are verified, those are now gold labels, which can be added to your data store as training data. You should then compute your test accuracy. If the model accuracy increases, you can deploy it and start using it in production. If it decreases, you should do some error analysis and model experimentation to see what went wrong. And in some cases, that may require doing some additional feature engineering on the label data that you added. In addition to adding data to your train set, you also want to regularly add data to your test set. So this is similar to the previous pipeline, except that instead of using active learning for selection, we want to randomly select queries here because we want to get an accurate distribution of queries and how they appear from user logs in the wild. But again, you would use bootstrapping to bootstrap initial labels, verify those labels to make sure that they are clean, and then add them to your data store, this time as test data. You can further speed up this pipeline by using auto-labeling, which is what it sounds like, labeling data automatically with an algorithm or model rather than manually with the human labeler. And Snorkel is a tool which enables auto-labeling. So you can use a combination of model predictions and user-defined rules or heuristics to label your data. And Snorkel essentially is a model itself. So you can abstain from automatically labeling queries, which this model has less confidence about. And that way, those queries can be sent to human labelers to annotate, or you can just ignore them. But either way, it allows for some model improvement without a human in the loop, which can be beneficial for security reasons or just for time and resource constraints. So that's everything that I wanted to cover today. Overall, we talked about how applied NLP is different from theoretical NLP. We introduced some NLP core concepts and fundamentals, discussed some best practices for collecting data, and which tools and frameworks you can leverage to train your models. And we walked through a quick tutorial on using these concepts to build a conversational interface. And finally, we discussed how to improve models in a secure way. So thank you for your time. Please reach out to me over email or LinkedIn if you have any questions. My contact information is written here, and I'm looking forward to hearing from you. Thanks.